Hi guys, welcome to lesson 9.1, quadratic graphs and their properties. Our objective for the day is to be able to graph quadratic functions in the form y equals x squared and y equals ax squared plus c.
This chapter has a lot of information to digest, so you should be watching these videos at least more than once.
Alright, first we're going to start off with our vocabulary. A quadratic function is any function that can be written in the form ax squared plus bx plus c when a is not equal to 0. This is the standard form for a quadratic function. So the parent function is the simplest quadratic function there is, which is simply y equals x squared. All other quadratic functions are going to be in a similar shape to this. They might be wider or skinnier, they might be higher or lower on the graph, but they are all going to follow the same shape. And speaking of the shape, we call these a parabola. That is the U-shaped curve of a quadratic graph. We've used that word before, but here is the official definition. Now, parabolas are symmetrical, so there is going to be an axis of symmetry, and this is the vertical line that divides the parabola into two matching halves, and it passes through the vertex. What is a vertex, you ask? Well, it is the highest or lowest point of the parabola. If a is greater than 0, the vertex is a minimum, and if a is less than 0, the vertex is a maximum. And we'll see examples of these in the next problem. So for problem 1, identifying a vertex, we are looking for that maximum or minimum point on the graph. So first of all, on graph A, it's going to be a minimum because the graph is opening up. We see the bottom of the graph there. And we just need to write the coordinates for that point. So our x-coordinate is -2, and our y-coordinate is -3. So it's a minimum, and it's at -2, -3. So for letter B, we want to find the vertex of the graph. This one is going to be a maximum. We can see that it's at the top of our arch, and the point is at -1 and 4. Okay. Letter C, what is the vertex of the graph? Is it a minimum or maximum? Our vertex is a minimum. It's at the bottom of that trough. And the point is at -2 and -3. On to problem 2. Now we're going to be graphing equations that are in the form y equals ax squared. We want to identify what the domain and the range are. Now let's refresh those vocab words. Domain is our inputs and range is going to be our outputs. So domain is our x values, range is our y values. So we always start with, let's just pick 5 points. We're going to go -2, -1, 0, 1, and 2. And when we plug these into the equation, -3x squared, we're plugging them in for x. So -2 squared is 4 times -3 is -12. -1 squared is 1 times -3 is -3. 0 squared is 0 times -3 is 0. 1 squared is 1 times -3 is -3. And 2 squared is 4 times -3 is -12. So now we just have to plot these points. Now the -2 and the +2, those are going to be off our graph slightly. This is a 10 by 10 grid. So Ms. Zirzo plotted our first 3 points. We've got -1, -3, 0, 0, and 1, -3. And she's approximating where the next 2 points are going to be. And now you just connect the dots with a smooth curve. All right. our domain, our inputs, we can put in all real numbers. And our range is going to be less than or equal to 0. So we see we have a maximum at 0. All of the points are going to be below that. There will never be a y value greater than 0 for this problem. All right, so let's take a look at letter B. We're going to graph the function y equals 1/2 x squared. And again, we're going to identify the domain and the range. So we put a couple points in there. We've got -2, -1, 0, 1, and 2. -1/2 squared is 4 times 1/2 is 2. -1 squared is 1 times 1/2 is 0.5. 0, 0.5, and 2. Notice we don't have to do the math for the last two because this is symmetrical. All right, so let's graph those. We have a point at 0, 0. We have a point at 1 and 1/2 and -1 and 1/2. And we have a point at 2 and 2, 2 and -2, 2. All right, and we can draw in our curve from there. And we just extend it up on the graph. Remember, we have arrows on the ends because they go off to infinity from each ends. We have a minimum here at 0, 0. So our domain is still going to be all real numbers. We can plug any number into this equation for x. But our range in this case is going to be greater than or equal to 0 because we have a minimum. All right. Letter C, we've got the function y equals 5/2 x squared. We're going to use our same inputs, -2, -1, 0, 1, and 2. And -2 squared, again, is 4. 4 times 5/2 is 10. All right, we've got -1 squared, which is 1, times 5/2 is 2.5. Or 5/2 if you like the fraction. 0 is still 0. And we're going to use that symmetrical property. And we're just going to plug in 2.5 and 10 for 1 and 2. So we put our points on our graph, -2, 10, -1, 2.5, 0, 0, 1, 2.5, and 2, 10. We have a minimum at 0, 0. So again, our domain is all real numbers. And our range is going to be greater than or equal to 0. So now we're going to compare the widths of some of these parabolas. And we see we've got 3 parabolas graphed here. We've got y equals x squared in the orange. That's our parent function. And we've got y equals
5x squared.
5x squared, and y equals 1/2 x squared. So the pink one is on the outside, and the green one, 5x squared, is on the inside. So what we can notice from this is the greater the magnitude of the number that's being multiplied by x squared, the more steeply or the narrower that parabola is going to be. It's going to grow much, much faster. So now we're going to just put these in order from the widest to the narrowest. we've got f of x equals negative x squared. We've got f of x equals 3x squared. And f of x equals negative 1/3. So we said our widest is going to be the one that has the smallest magnitude. So we're going to start off with the negative 1/3 x squared. Okay, our next widest one would be the negative x squared. And our last one would be the 3x squared graph. Okay, we don't care about the signs on this, we just care about the magnitude of that amount, the absolute value of it, whichever one's going to be the greatest. So, second question, what is the order from widest to narrowest again? So we're going to start with that one that has the smallest magnitude, which looks like it's going to be negative 1/3 x squared again. We go to our next largest one, which is going to be 2x squared. And we've got our last one, which is 4x squared.
Might be a good time to stop the video and watch it again.
All right, problem 4, we're going to graph equations that are in the form y equals ax squared plus c. So we've got our parent function there, y equals x squared, so we can graph those points pretty quickly. So we've got negative 2, negative 1, 0, 1, and 2 as our inputs. And for y equals x squared, we've got 4, 1, 0, 1, and 4 as our outputs. So we can go ahead and graph that one. So we have points at negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, positive 4. Okay. So we have those two. Now we're going to graph our second equation, y equals x squared minus 3. All right, so when we plug it in, we're going to get 1, negative 2, negative 3, negative 2, and 1. So as Ms. Zirza is going, you can see that using the exact same inputs for these two graphs, all we've done is we've subtracted 3 from our original. Our parent function has moved down 3 units, so each and every point is going to be 3 units below the corresponding one in the parent function. All right. So for letter B, we've got y equals 2x squared plus 4 and y equals 2x squared. So we'll start off with 2x squared plus 4. We plug in our numbers and we're going to have 12, 6, 4, 6, and 12. So we can go ahead and graph these. Again, we're going to have two that are going to be a little bit off of the grid. That's all right. Okay, our second equation, y equals 2x squared. We do our coordinate table. We're going to have 8, 2, 0, 2, and 8. So we go ahead and graph those. And we see this whole pattern holds true yet again. One thing to notice is when we have things, when there is no middle term and it's just 2x squared plus 4, that plus 4 tells us where our y-intercept is going to be. We are 4 units up. For problem A, it was at -3. We were -3 units. That tells you where that y-intercept is going to be when it's in this form. Now, our last problem for the day is going to be using the falling object model. And in this model, we have an equation that's given to us. The height is equal to -16t squared plus 70, where the plus 70 is our starting point above the ground. And h is our height, and t is the number of seconds that have gone by. So we're going to measure, we set up our graph. Remember, a good graph needs to have labels, it needs to have units, and we need to have a consistent scale. So for our x-axis, we're going to go up by half a second per line. We're only going to mark the whole seconds here. For our y-axis, we're going to go up by 5 feet per line, and we're just going to skip around here a little bit just so we have a little more neatness on the graph. But each line is going to be worth 5. All right, so we can start off. We're going to, at 0 seconds, how high is that acorn? Well, it hasn't dropped yet, so it's at 70 feet. And when we start plugging numbers in, if we put in half a second, so after half a second after it drops, it will be at 66 feet. 1 second, it'll be at 54 feet. 1.5 seconds, it'll be at 34 feet. 2 seconds, it'll be only at 6 feet. And by 2.5 seconds, it would be -30 feet. Well, we don't need to worry about that because we're hitting the ground and not a giant hole. So we can go ahead and graph these points. We start off at 70, and we have a point at 66. You're going to be approximating on these, so it won't be perfect, but that's all right. And we can see from the way the graph is shaped, we have a maximum at 0 seconds and 70 feet. And about the question we're asked is, about what time does the acorn hit the ground? Well, from the graph and from our data table, we can see it's about 2 seconds after it falls. A little over 2 seconds. All right. Letter B, we have a child dropping a pebble from a height of 30 feet above a lake, and the equation -16x squared plus 30 gives us the height of the pebble in feet after t seconds. We want to graph it and then figure out about when that pebble is going to hit the water. So we set things up the same way. We're going to go by 2's on our y-axis.
Hold on, Mrs. Zurzo can't count by 2.
24. No. And on our y-axis, we're going to go by quarter seconds. So we're going to skip and just kind of do some of the bigger ones. So 0.5, 1, 1.5, 2, and we can stop there. All right, so at 0 seconds, that pebble is 30 feet off the ground. At a quarter second, we're at 29 feet. At half a second, we're at 26 feet. At 0.75 seconds, we're down to 21 feet. At 1 second, we're down to 14 feet. At 1 1/4 second, we're at 5 feet. And at 1.5 seconds, we're at -6 feet. So we don't need to worry about that since it's off the graph. So the question we were asked was approximately what time does the pebble hit the water? And it's going to be approximately 1.25 seconds. All right. And that is for the lesson for today. We'll see you guys in class tomorrow.